All right, let's take a look at exponential growth and decay models. You should have a page that looks just like this that you can write some notes on. So we want to be able to understand how to identify when data that we have is exponential and then be able to write equations for it as well. I've tried to throw one in here that gives us a little bit extra to think about. The first thing we want to talk about, though, is a common ratio. Since exponential functions are about multiplying by the same number over and over again, then the way that we identify what that number is that we multiplied by is to divide the result by the number before that and figure out what that number might have been. The first thing we have to do is make sure that we have been multiplying by the number the same amount of times, and so we want equal spacing in our x values up here. And we can see that every time these are going up by 2 every time. So I'm adding 2 there, add 2 to get there, add 2 to get there. That's going to make this a little bit tricky down the road, but it is important to be able to identify that this is exponential growth. And so, like we said, what we do is we take the result, we'll take this 16, and we'll divide it by the number that we just came from. So we were at 20, now we're at 16. The question is, do I progress along this table by multiplying by the same number every time? And by doing this division and getting a 0.8, it says the number you multiplied 20 by was 0.8 to get 16. And so then the question is, well, does that continue? If I do 12.8 divided by 16, I also get 0.8. So this is telling me that, yeah, what's happening here every time is I'm multiplying by 0.8, so that is the characteristic of an exponential function. Now, I might want to get an equation for that. Okay, so this is where the skipping by 2 across the top instead of by 1 becomes a little bit trickier, because this number 0.8 is definitely the number that I'm multiplying by over and over again. Okay, but if my input is 2, I only want to actually multiply by 0.8 one time. And I can see that in my table here. This is one time multiplying by 0.2. If my input is 4, I want to multiply by 0.8 2 times. If my input is 6, that's multiplying by 0.8 3 times. Okay, so if my input is 2, that's one time I'm multiplying by 0.8. If it's 4, that's 2 times. If it's 6, that's 3 times. Well, this list of numbers over here is just the first list divided by 2. So this in my power here is going to be x divided by 2. So again, to get out to the 8, I would have multiplied 4 times, 1 time for this first arrow, 2 times, 3 times, 4 times that I've multiplied by 0.8. But what did I multiply by 0.8? Okay, so I know that my equation is going to look like y equals some starting value times 0.8 to the x over 2 power. Okay. And I can pick any point in here. So let's pick, for example, this point. And so this says when your input is 6, the output should be 10.24. So we'll put a 10.24 equals a, and this is the thing that we don't know, times 0.8 raised to the x over 2 power, and my x is a 6. So that says I should get a 10.24 as a result of multiplying some number times 0.8 to the 3rd power. So I'll go to my calculator and figure out what 0.8 to the 3rd power is. That's 0.512. 0.512 times the a, that's my variable, that is over there, and this is equal to 10.24. So a little bit of division, 10.24 divided by 0.512 gives me 20. it tells me that the answer to this problem should be, or the equation that predicts this table is y equals 20 times 0.8 to the x over 2 power. I can test that in a number of places. I may also notice that the 20 is exactly this 20 that we started with from the very beginning. Okay, so if we know where the starting point was that we started multiplying by 0.8 over and over, that probably would be an easier way to come up with that number, but I showed you this just in case you don't know where that is. Okay. So I'm going to take this, slide this equation out of my way a little bit. My work got big here, and I want to get it out of the way so it doesn't interfere with my next problem. So I'm just going to shrink that down a little bit. Okay. And let's take a look at the next problem. So the population of elk using a feeding station last season was 596 individual animals. This season they were able to identify 638 elk at the feeding station. Assuming that there's exponential growth because the elk are reproducing, then write an equation to predict the future population of elk at the feeding station. Okay? One of the beautiful things about exponential equations is you can start them anywhere that you want. You can decide, what am I going to call the beginning? So it's like I'm making a table like the one above here, where the x, okay, again, so it's like the x is the inputs, and we can say that last year was 0. So we'll say last year was 0, and the population of elk last year was, I'm looking at 596. And then this year, which would be what we'll call year 1, so our equation will predict things since the year that there were 596, and this is 638. And so we can do the 638 divide by the 596. If we're assuming exponential, then it means that there must be some number that I'm multiplying by every time. And so I'm asking the question, the other way to think of this is, what did I multiply 596 by to get 638? Okay. Well, that's a simple enough equation to solve. So 638 divided by 596. We're going to have to keep several decimal places on this. I'm going to go out to 4 of them for these population kind of problems. So to 4 decimal places, this is a 1.0705, which means, incidentally, that the population is increasing by about 7.05%. Okay. So our prediction is a 7.05% increase per year, and our equation, if we wanted the population of elk after T years, is going to be the population of elk at the beginning, which we use 596 for that. I need to move this up here where I have a little bit more room, times the number that I multiply by every time, which is a 1.0705. Okay. And I'm going to raise that to the T power for T years. And this equation now would allow me, assuming this growth continues at about this rate, then this would enable me to make predictions about how many elk I'm going to see next year and maybe 5 years down the road. That would help with the planning of how much hay I need to have around to feed them as they show up, for example. Okay, so there is one example of exponential growth. We were able to write an equation based on a story. Okay, a little bit more to go here. All right, the next story. Everybody loves a supercar except for the people that bought them brand new and are now trying to sell them a few years later. Okay, so we'll have a story about a particular Lamborghini that is known to depreciate, okay, at a rate of 18% per year, which means that the value of the car goes down every year because it's not brand new anymore. and people tend to drive them very hard when they're supercars. Every once in a while, someone might just park them, but what's the fun in that? Okay. So let's say that this car sold for $560,000 when it was new. We're going to write an equation to predict the value of the car after T years. Okay. This general form of A times B to the X, we also looked at that as the B being able to write that as 1 plus R, and we'll go T or X doesn't really matter there. Okay. Where this is the 1 plus R is the growth factor and R is the growth rate. Well, in this case, it's giving us an 18%. We never use percents in problems. We always change them into decimals. And in fact, since this is depreciation, that gives us an R value of a negative. Okay, so again, R is a negative 0.18 because this is depreciation. And if we follow this pattern, then the A is the initial value. Oftentimes you'll see this written as an A0. So the value of our Lamborghini after T years is going to be the $560,000 that we paid for it new, or somebody did, times 1 plus negative 0.18 raised to the T power. Or in other words, 560,000 times, what's that, a 0.82, sorry, to the T. We recognize that as exponential decay because the B value, the number in there, is now less than 1, is less than 1 because the 18% was negative and subtracting it from R, so that forced this to be an exponential decay. So with this formula, you could do things like maybe try to predict in 10 years, would you be able to afford this car? If your budget for a car is $30,000, how long will it take for it to get down to a value of only $30,000? And then you can decide if you still want it at that point. All right. One last bit on this. I know this is getting a little bit long. Okay. We do want to talk, however, about... All right. So in order to encourage people to invest money, a lot of times what a bank will do is they'll offer a percentage rate, but they then offer to compound it more often than just once a year, which means that they're going to calculate the amount of interest that you earn on maybe a monthly or a quarterly or maybe a daily basis instead of waiting to the end of the year to give you your interest. Now, of course, they're not going to give you the whole, if it's like we say here, 6%, they're not going to give you the 6% every day or every week or month or quarter. They're going to give you an appropriate percentage of that. So, for example, if it's compounded monthly, there are 12 months in a year, so they would take your 6% and divide it by 12 and get a 0.5%, and they're going to give you, well, 0.5% doesn't have the percent sign on there if I do that. So they're going to give you 0.5% every month. Okay? And this ends up being a little bit better than 6% as you go along. Of course, they do this on the other side when you're borrowing their money in terms of like a credit card. They definitely compound that every single day. Okay? And it's a high rate to begin with, so stay away from that garbage. Things that we need to know about this formula. This A sub 0, this is the initial amount. Right, because initial implies at time 0, and if we put a 0 in for the time variable up here, this is all this stuff to the 0 power, which we know is equal to 1, and 1 times A0 would be the A0. Okay, the R is the annual interest rate. and the N is the number of compounding periods in a year. Okay, so we start with an annual interest rate, a whole year's worth of things. So if we say it's compounded monthly, then N is 12. If it's compounded daily, then N is 365. If it's compounded quarterly, which means every 3 months, that happens 4 times in a year, so the N would be 4. The N shows up there. The N also shows up here, because if you're just going for 1 year, you're going to make that multiplication 4 times. Okay? That annual interest rate, of course, has to show up as a decimal, not as a percent. Okay, so for example here, if I invest $2,000, that's my initial amount, okay, in a company that averages 12% return. So I found some investment that gives me a 12% return. That's a 0.12 as a decimal, compounded quarterly, which means 4 times a year. Then how much will that be worth after 25 years? Well, I'm going to do the 25 times the 4. So the value of this investment at the end of 25 years is going to be 1.03 to the 100th power. And I have to go to my calculator for that. I can't multiply it by 103 or 1.03 100 times in my head. If I take that to the 100th power and multiply that by the $2,000 that was in there to begin with, this will be worth about $38,437 and 26 cents. Okay. Now, the cool thing about that is that I only invested $2,000. You may look at it and say, well, $38,000, it's not like I can buy a Lamborghini in 25 years with that. But all I ever did was put $2,000 down and wait. I never put any more money in this. All I did was when they calculated the interest, I let them keep the interest and add it to the balance in my account. Okay? And so this is almost 20 times the amount of money that I started with. Exponential growth is very fast, but it doesn't feel fast right at the beginning. You got to let it go a little bit and build up some momentum, and then it goes crazy fast. So that is the end of our notes on that, and I apologize for the length of the video and the number of times that I had to stop and restart it.